Hi and good morning. And today's the 2nd of March 2025, and we like to do these webinars once a week, and it's just answering technical questions that have come in during the week. So we speak quickly, or rather I speak quickly here because I just want to get through the questions and sort of make sure it's efficient for people. It's about 7 questions. So question number 1 is how do I perform foot of wave analysis? They say in a non-catalytic system. I also did say that at Zimmer and Peacock, because we tend to do analyte analysis, we tend to do sort of bioanalytical chemistry, or bioanalytical electrochemistry, if I can maybe call it that. Foot of wave analysis is not something that we do an awful lot of, but I thought it was an interesting question and I will answer it this morning, so I will do that. Also, somebody sent me some immuno data. I think they're mostly concerned about reproducibility, and they're also concerned where's their signal coming from. So I'll answer that, which is interesting because they give me data, but they haven't given me their electrochemistry. So the question, where's their data coming from? I can only figure that out by assumptions, which I'll make those assumptions today. Somebody else is interested in chloride sensors for sweat. I've put together a bit of a landing page for them, and they can purchase various technologies from that landing page, and that'll give them what I call technology readiness level number 3. They can do a proof of principle in a lab. There's a big lift on going from lab experiments to wearable biosensors. But I was just talking to somebody just at the end of Friday, a really large billion-dollar company, and we were talking about the cost to make wearables, and we were talking about sort of companies like BioLink that have spent like 154 million doing a continuous glucose monitor. So I'm always really cautious about companies that approach us about wearables, because you do need a certain amount of funding in order to do wearables. Otherwise, it can just be conversation, and actually nobody can do anything because there's just not the revenues, but the funding in place. Somebody else is interested in measuring peracetic acid. It's probably worth saying that on the ZP website, just of recent, I have been doing some tests on milk, and I will make up some peracetic acid, or rather I'll do some peracetic acid testing this morning. Oh, I've forgotten to add this one, so I missed this, but ZP is doing a spectrometer for light analysis, but that's not yet released. If companies have a budget and they want to do light work with us, they can, but we need some evidence of budget first of all. Talk about making a glucose sensor on a ZP, or at least I'll show you some glucose data on a ZP screen printed electrode, and then also how to design a screen printed electrode. I'm just helping somebody with I call it offsetting contact points, but that'll come in a minute. So if you can spot your question among these questions, then that will help you jump forward and find your video. So the first one is, or your section of the video, first one is foot of wave analysis. What I might just do is just go to my camera here for a second. I'm just going to grab a ZP electrode, which I will do. And I'm actually going to grab some ferricyanide. I'm just going to turn around and grab some ferricyanide for a second. Ferricyanide may be appearing later on as well when I make I'll make some comments later on about an immunoassay. I think that's in question number 2. And I've got a strong suspicion that in the immunoassay they're also using ferricyanide or ferrocyanide. I'm just going to scan a QR code. This is also relevant to the person doing peracetic acid analysis as well, that this instrument will feature later on there as well. I'm just going to put a name in for this. So this is ferricyanide. By the way, I'm using the Sense It All potentiostat to do this work at the moment. The good thing about the Sense It All potentiostat is it's an instrument that can take people from lab experiments to minimally viable sort of product prototype very quickly. So many instruments are just so lab centric that they've no way of really translating to be a real world application. But I'm just going to do a quick bit of cycling voltammetry, which I will now do. I will continue. Start here, do that. I'm going to do this quite quickly, so this will be, that'll do. I'm going to do this quite quickly. So at ZP, we do quite a lot of cyclovoltammetry. It's interesting because in question number 2, they actually have a problem with sort of reproducibility. And we actually use cyclovoltammetry a lot when we're actually trying to prove to ourselves that our manufacturing is, essentially reproducible. So what I'm doing here now is I'm just gathering its current versus time. If you most cyclovoltammetry, they actually show it as current versus potential, which I will also do as well. But it's actually gathered as current versus time. It's just people don't see it in that perspective. And I think it's actually quite useful to sometimes see your cyclovoltammetry as current versus time. And the time it takes is obviously proportional to your scan rate. So there's kind of an extra. So it says here that the data is uploaded. The way the ZP system works is, if I just share my screen with you for a second, screen 2, I'm just going to do a quick refresh on that. I should have given that a slightly more distinctive name, but let me just give it a quick refresh. So every time we do an analysis on the SenseIt platform, it will say data uploaded, and the data will go to the cloud. So I can see my experiment here, and I can have a quick look at my cyclovoltammetry. So this is probably one of the only, there it is. I can see my CV here. Here's the first scan, here's the second scan. So I can see my scan here as well. The reason I did that was because with cyclovoltammetry, there's kind of 3 regions. You've got the foot of the wave, which this person's particularly interested. Then you have a mixed region where you've got what we call kinetic control and mass transport limitation, and then you've got a sort of peak in cyclovoltammetry where you become diffusion limited or mass transport limited. And this person's interested in understanding and analyzing the foot of their wave, which I have some slides on now. So I'll do some foot of wave analysis here. So at ZP, this is really pertinent to question number 2 as well. We do a lot of analysis on our screen printed electrodes during production. And we do use a lot of CV because it's a good way of actually kind of making sure that the quality is good enough for us and good enough to also ship to our clients as well. But in this particular case, this person's not interested in our quality of manufacturing. They're interested in how do I analyze this section of the cyclovoltammogram. I often call it the kinetic region, where the concentration and the rate at which material is having to diffuse or mass transported to the electrode is not the limiting factor. It's simply just the potential that the signal is increasing proportional to potential. So you can, here I've shown the sort of, where I want to get to is kind of a Tafel plot. Because in a Tafel plot, I can use the slope and the intercept to sort of tell alpha, which is alpha, theoretically for a reversible system, alpha should have a value of 0.5. And then I have the exchange current, or the log of the exchange current, which is the higher the exchange current, then essentially more reactive or more current per molecule I'm going to get for that particular oxidation in this particular case. So exchange current is kind of rate of reaction, really. Now, the first thing that we do is, I have a cyclovoltammogram here, and I know which region I'm interested in. So I actually just go and, grab the data from that particular region. Now, you can tell by the formatting that I've done this in Excel. I am thinking about how to actually write some, either doing this in Julie, which is an online database that we have, or Julie plus some Python scripting, because it's a bit manual the way I did it. But like I say, it's not something we do a lot of, but I've done it in a very manual way. All right, so I've got my full, let's say, set of data for my particular experiment, but this person doesn't want to analyze the mixed region or the mass transport region. They actually just want to do the foot of wave analysis. So you can see here, I've just essentially grabbed the data that I think looks primarily like the foot of wave. And then what I've done is I've actually I'm starting to move it into SI units, because the units in my voltammogram were microamps. So I just divided it by 1 million to get it into amps. And then I realized that, in fact, in the sort of true Tafel plots, they are using, I don't know why I did that, but they actually use current density. So I had a look at our electrodes. In fact, the data was coming off what we call a 501. These are really repeatable electrodes. So question number 2 today, they're suffering from repeatability. I think ZP is we put a lot of effort into repeatability. I think we do a really good job on it. It's not something anyone even talks about. I don't know why. Anyway, so we were using these 501s. So I had a quick look at the area of the electrode. And so what we're doing then is that was the diameter, by the way. Then from there we could work out the area. It's ridiculous because I'm doing it in meters squared, but I'm trying to keep everything in SI units. So that's why, so I've gone from microamps to amps, and then on the next slide, I actually go from current in amps to current per meter squared, because I've divided by the area. So I'm just keeping myself in SI units, and now I'm in current density. Now I'm getting close to the Tafel-like plot, because in fact now I do the log of current density. And this is kind of more classical now. You kind of have a linear region, and then the log of 0 is essentially non-calculable. I don't want to say it's infinity, but it's non-calculable. And so it starts to curve off as we get to 0, and it gets a bit messy down here, but it's okay because I only really want this region here. So I sort of zoom in on that region, just grab the data from that. I do a linear best fit in Excel, and I get the equation that the log of current density is equal to 15 times, now I'm using potential here, not over potential, minus the log of exchange current density. So I can use that 15 here is actually proportional to this statement here. Now that statement, we know most of the values in that statement because N is number of electrons. In this particular case, I was doing the oxidation of ferrocyanide, so N was 1. Faraday's constant is 96485, I think, coulombs per mole. R is the gas constant, which is about 8.314. And T is temperature, which is in Kelvin, which is about 298, so room temperature. So those F over 2.303 times R times T is equal to 16.91. Now what that means is that alpha in my case must be equal to 0.88, which is ridiculous because, not ridiculous, but you shouldn't really be able to get above 0.5, I believe. Now the reason it is I realize what we do is, because we're not so interested in the foot of wave analysis. It's not super interesting to us at ZP because we want to do solution analysis. We're not interested in the analysis of the, let's say, electrode itself. We actually scan quite quickly, so I realized that I've got a contribution to my current, which from this analysis you could easily argue is actually about 30%. So I've got 30% more current, I would argue, in my cyclophotometry data that's actually coming from the charging current, because we're actually scanning quite fast. I'm scanning like 100 millivolts per second. Now I do that because I'm not that interested in foot of wave analysis, but I realize that when people are actually doing corrosion studies and battery studies, I think they're actually scanning a lot slower than that. So that's why I'm getting more than. But if I was to say what I've done, I've taken the cyclophotometry, I've narrowed in just on the foot of wave, I've turned my current from microamps into amps, I then turned my current from amps into current density, I then just plotted the log of current density versus voltage. I found the linear region, I fitted it, and then that gradient is proportional to alpha over NF 2.303 RT. And then my intercept, which I haven't touched upon here, is actually proportional to or equal to the log of exchange current density. In this particular case, it's just 10 to the power of minus 2.4902, which is 0.0056 amps per meter squared. So that's my analysis, or my performing of a foot of wave analysis. And I find it really interesting actually, because this is like real world data. Oh, and I didn't quite get the alpha that I really was expecting. But then I realized, yeah, because we scan quite quickly, so there's a contribution to our current which is not. And then I remember I had a colleague, he was doing his PhD, and I remember he was doing corrosion. He used to scan really slowly, and I was like, yes, because then he wouldn't. A, it was probably more informative for him, and B, it would also just eliminate that contribution from current, charging current rather. Now, question number 2 is about immunosensors. So hopefully you can jump ahead if you're not interested in the first question, and you find yourself here at question number 2 about immunosensors. What we find here is this is some data that somebody has sent me. They have readings without analyte, and they have readings with analyte. Now, that analyte is 1 microgram per mil, which is quite a lot actually for a immunosensor. That's a lot. So they may actually part of their signal may be due to non-specific binding, and as well as specific binding, but that's not the question today. They say trouble in uniformity. I think reproducibility and repeatability, and really these are terms that ZP has defined, but that's probably part of the sort of problem in biosensors. People don't necessarily know the manufacturing language, let's say. No criticism of this person, but it is something that, this is not necessarily about uniformity. This is about repeatability of experiment. So they have 3 data points without analyte and 3 data points with analyte. And they're concerned about their reproducibility. And I think it starts off with the underlying electrodes that you're using are probably not as reproducible as you would like. This is the biggest problem in biosensor development world, that people think that the screen printed electrodes they're getting. I had a gentleman the other day. He's not going to buy screen printed electrodes from us because, in fact, he can find them, let's say, cheaper elsewhere. And that's a real problem because, in the R&D phase, he can find electrodes that are cheaper elsewhere. But he's going to basically come into this problem that he doesn't actually have a fundamentally reproducible screen printed electrode. So that is a big problem with people who are developing biosensors. Then after that, somebody is functionalizing these electrodes to be an immunosensor. Functionalization is a multi-step process. That is definitely a source of reproducibility concerns when making biosensors. At ZP, we are ISO 13485. We have air-conditioned labs, we have robotics, we have calibrated pipettes. I've said robotics already. Calibrated balances. Everything is really controlled to make sure that we can get reproducibility of functionalization. I think startups and academic labs really struggle with that, but it's not a criticism, it's just a fact. And then the other part of reproducibility is actually the operator themselves. Are they able to bring solutions to electrodes, in a repeatable manner? Is the sequence of starting the experiment exactly the same every time? I suspect that unless everything is controlled, reproducibility is a problem. So I suspect that their lack of reproducibility is a stacking of problems. It starts with the electrode, then the functionalization is probably not reproducible, then the test may not be reproducible. But in the end, they do get a signal. Now, the reason I think they get a signal is because the higher your concentration of analyte, the more forgiving overall the system will be, because you've got so much analyte that even if you make irreproducibility issues, you just got so much analyte, you will still get a signal. So they definitely have a signal. They have data for no analyte and data for analyte, and by eye you can see that these two things are separated. I suspect if I did a t-test, which I haven't, I would find out actually this data wouldn't be able to be separated necessarily by a t-test, but I haven't done that t-test, so they actually may be separable by statistical analysis. Now they do ask what these square wave peaks signify in the graph. Well, to really answer that question, people would have to tell me what the biochemistry was, but I've kind of taken a guess at it because it looks a little familiar to me. That I think they're probably on a gold electrode. They are not on a ZP gold electrode. They are not. So don't think that the reproducibility is coming from us. Pretty sure they're not on a ZP gold electrode. But with an electrode, you put the sort of your immuno material on top of the electrode. You may put a blocking layer on there, and then you may have the binding. So first of all, you sort of manufacture the immunosensor. So I think they've got a reproducibility problem here. Then you bring in your target. I've shown some antigens here. Now the source of their signal is, I think that they're using possibly either ferrocyanide or ferricyanide. It doesn't really matter because they're starting their voltammetry at a potential where if they add ferricyanide, it actually becomes ferrocyanide. So then they're actually reoxidizing ferrocyanide back to ferricyanide. They may be actually adding deliberately ferrocyanide. Sometimes people do a 50-50 mix because I think they're not really sure of what is happening with my electrochemistry here. But you could do this kind of chemistry by having just ferrocyanide, and you then sort of in adding ferrocyanide, it's already in the reduced state. They scan to a positive potential. They oxidize the ferrocyanide to ferricyanide and they get their signal. If they added ferricyanide, it actually ends up at the negative potentials where they start. It ends up becoming ferrocyanide, and then they reoxidize it back to ferricyanide. So the source of their signal is, I think they've got a redox molecule, which is some form of ferrocyanide that's trying to get to the electrode. But when they've got high degrees of blocking, they only get a tiny signal. Or they get a smaller signal. Actually, they get quite a significant signal when I think about it, actually. And then later on, in some of their experiments, there's not so much antigen, and at which point it's easier for the ferrocyanide, for example, to access the surface, and they get a higher current. So I think the source of their current, this is just speculation, by the way, because if somebody hasn't told me what the electrochemistry is, I can only just guess at what's going on here. But, this is my guess as to what's actually going on. That's the source of their signal. Okay, so reproducibility, you fundamentally don't have a reproducible screw-fed electrode. The pipetting steps, when you're trying to functionalize that probably by hand, are probably not reproducible. The testing steps, unless everything is really controlled in terms of time and temperature of test, then you've probably got reproducibility issues there, and all these things stack on top of each other. You do have a signal, but you're probably, I don't want to say getting away with it, because you've actually got 1 microgram per milliliter, which is actually quite a large amount of analyte, especially for immunosensors. They're generally, people are very interested in kind of quite low concentrations, nanograms and picograms of this kind of material. So micrograms seems quite high. Okay. So in summary, I think this is the oxidation of ferrocyanide to ferricyanide, but they haven't told me. I'm just kind of, I don't want to say guessing there. Chloride sensors. Somebody's interested in making wearable chloride sensors. I have put a landing page together for them with microfluidics, chloride sensors, electronics, test solutions, and rinse solutions. And I have put a link. So I'll put a link underneath the video as well so that they can find that. I know that you can there is a technology on the market for measuring cystic fibrosis in children, and I'm pretty sure they're measuring the chloride in sweat in that particular technology. Somebody else is interested in measuring peracetic acid. Now they sent me some images. I created my own images. The good thing about screen-printed electrodes is they're really electrochemical cells. So if I hold this, I'll hold one of these up. What we have there is really an electrochemical cell that kind of has a working electrode in it, a counter electrode in it, and a reference electrode in it. And so, it's really equivalent. The good thing about a screw-printed electrode, though, is that you can really reduce the size of that electrochemical cell. When I did that ferricyanide experiment earlier on, I was only using 50 microliters. In a minute, I'll do a quick test on some milk and some peracetic acid, and there again, I'll only be using 50 microliters again. Now, they do have these technical questions about membranes and stuff, but I mean, at ZP, we're already, and I'll do a peracetic acid experiment at the moment. So people kind of have this kind of, you're an entrepreneur, you want to get to market, and people think that the barriers that they have are actually technical. But I actually think that the biggest barrier that most people have getting to market is financial, and it's the ability to persuade people that what you're working upon is valuable enough that they'll invest in it. So I think that actually we can get people to market quite quickly measuring peracetic acid in milk, for example, but there needs to be essentially a budget in place. So it's not about the technical questions. It's about, is there a budget, and if so, will you spend it with somebody like Zimmer and Peacock? So I'm just going to do a quick demo for you, in fact. This is a very powerful platform. Earlier on, I did some cyclovoltammetry. It's also a platform that allow people to develop new assays. So, for example, here's one for caffeine, but I'm going to do a bit more of a fundamental assay here. I'm actually going to use amperometry. So now I'm in amperometry mode. I'm just going to take off that electrode. I'm just going to grab a clean sensor because the person asking the question has kind of sent me images of screen printed electrodes and sensors and stuff. So I just want to kind of say, the images you're sending me, here you are. Right, I'll take one of those. I'll put it into the potentiostat. People are very interested these days in developing potentiostats. Potentiostats are commoditized items. You don't add a lot of value in building potentiostats. If I look for potentiostat vendors in the world, I'm probably going to find there's 50 of them. So there's just not a lot of value in it. It's really doing the application, getting the application in front of real users, finding out what they like, finding out what they don't like, and building a customer base. These are really the challenges when it comes to developing new assays. I know that some entrepreneurs in the US now, they're kind of, whether their go no go on an idea is, can I find my first 100 customers? And actually it's really good because we think that the challenges are engineering, but actually I'm going to show you that the challenges for making a peracetic acid sensor for milk is not engineering. So what I'll do is I'm just going to take 50 microliters of some milk, which I have done. I am just going to label it up in the app so I can find it. Again, I'm using this Sensi All platform, peracetic acid. Right, so I've done that. Right, I'll go continue. So I'm going to just put some parameters in here. That might be enough. Yeah, that's probably enough. I'll just change the time slightly. Right, I think I'm doing this quite spontaneously, so bear with me. I'm just going to grab some peracetic acid. I have done other videos on this as well where I actually prepared the peracetic acid. So I've got some peracetic acid here. I'll just put it into a little pipette and then I'll hit go. The electrochemistry, by the way, this person's also interested in optical as well. The problem with optical systems, and ZP does have an optical system, problem with optical systems is the sample has to be transparent. There's something fundamental about many real-world samples. They are not transparent. If you want to make a low-cost, easy-to-use assay with very little sample prep, hey, no sample prep, I've just put the milk on there. It's probably electrochemistry, actually. Right, so we go start. So I'm analyzing this now. I've got my signal coming in real time. Now what we do at ZP then is we take these kind of fundamental proof of principle sciences, or experiments rather, and then turn them into a QR code, and then they can become the customer's QR code so that they can sort of roll the technology out for their customers. All right, so I'll let that go about there. I'll put a little, I'm going to put just a tiny drop. I'm not going to put this whole, I'm putting just touching it with a drop there. So I literally just touched a drop onto that, really a tiny amount, and you can see the signal already. So that tells you that what that tells you there is electrochemistry using screen printed electrochemical technologies able to detect peracetic acid in my sample? The answer is yes. So you don't need to go off and necessarily develop new electrodes. You don't have to go off and develop potentiostats. That's done. So that's kind of moved, people would spend 2 years getting to that stage. The next stage is make it better, make it, make the assay better, make it reliable, make it reproducible, make the user experience good. But fundamentally, that is the detection of peracetic acid in milk. And then it says on my little screen, upload complete. So I just want to kind of show you what that upload complete actually means. So I'll share my screen with you now. I just worry that sometimes people are kind of reinventing the wheel and sort of, things that can already be achieved. I think what the world requires is applications. What it doesn't require is like lots of engineering in order to build new platforms and new hardware to then make that application work. It requires the application. That's where the real value add actually is. So really at ZP, our whole mindset is how do we get people to market as quickly as possible? And that's why we've kind of built these kind of platforms. So here we are, peracetic acid. So I can see it in our database, and it's been uploaded. So essentially I just did a baseline and then I added the peracetic acid just to give you confidence that we generally can see a signal for things like peracetic acid. I mean, I can even go in there and I can sort of do some let's find the peak height. Let's find that peak height at about 50 seconds. Just have a quick look at what that looks like. There we are. So I found the peak height there. I could even then be, sort of saying, okay, now I've calibrated my system. I'm gonna make up some numbers at the moment. Just this. What I can show you then is I can start turning. In fact, I need to show values. Show extracted values. There we go. So now I need to increase that a little bit, but I can start to figure out the concentration. And in fact, I want to put it in ppm actually. Yeah, I'll do that in ppm. So you can see very quickly we can start working on actually how to turn the raw signal into something sort of meaningful pretty quickly, and actually start displaying in the units that would actually be useful to the end user. So at ZP, if somebody has the interest in doing something like peracetic acid in milk, it's not such a barrier as long as they're on the SenseIt platform and they're working with ZP to actually turn the idea into a real world assay quite quickly. I just made that up, but 0.962 ppm, and we can actually send that value then back to the phone. So that was a quick demo on how powerful the SenseIt potentiostat and SenseIt platform is. SenseIt potentiostat is a device that's really developed to go from scientific experiment to real world application really quickly. Somebody's been making what I call a generation 2 glucose sensor on our system. So they've been taking one of our screen printed electrodes, they've been modifying it with mediators, and then making a generation 2 glucose sensor from it for continuous measurement of glucose. This is not my own work, but they've been doing some nice work, and actually they are able to make this work. They've been testing it with glucose, testing it with hydrogen peroxide, and actually getting some quite nice results out of it. So I appreciate you sharing that with me. And another good tick. People who are on our platforms are actually making some really good progress. I think sometimes other people are kind of struggling a little bit because just the fundamental screen printed electrodes are not reproducible, but this person's actually making some really good progress. So thank you for sharing that with us. I'm also helping somebody else at the moment understand that our screen printed electrodes have many design advantages. One of them is that actually we don't make electrical contact with the working electrode right next to it. We actually have quite a distance. And therefore, when we sort of functionalize and put a drop on there, we're not risking exposing reactive metals to liquid solutions. So I think some screen printed electrodes, they have failure modes that we don't have at ZP because we've actually designed it out. So I apologize because I didn't talk about the spectrometer, but in reality, I think we need to talk. We do have a spectrometer in an application of milk, which is why I was going to talk about it. Actually, I think the problem with milk is you'd have to dilute this sample up quite significantly to be able to shine light through it. So spectroscopy seems like not a great idea for that particular application. But I did do footer wave analysis this morning. I did talk about immunosensors. I had to speculate as to what their signal was because they didn't tell me the biochemistry, but I gave them my best guess. I've Chloride sensors for sweat analysis, for cystic fibrosis, no probs. I put a landing page together. I even did a measuring of a peracetic acid. I forgot the spectrometer. I did talk about making a glucose sensor, and I'm trying to help somebody at the moment design a better screen printed electrode. And intrinsically, ZP, I mean, we've been making these screen printed electrodes now for 10 years. I actually started my career with screen printed electrodes in 2000, so that now puts that at 25 years. So there's a lot of tricks and tips built up in our screen printed electrodes, which are really hard. And what's different about ZP is that we genuinely are the biggest users of our own screen printed electrodes. So we're making the screen printed electrodes that we sell as good as they can be, because we directly benefit from it. We're the only company that has that kind of business model where we're the biggest users of our own products. I think the analogy is, it's like going to a restaurant and finding out that the chef and all the staff are just in the front eating all the foods. That's what we're doing. And then there's clients also at other tables, but we're also in the restaurant eating away as well. If you do have any questions regarding asking technical questions, we are I'm answering some academic questions at the moment. So we do tend to help academia because the funding is low and people are trying to learn. If these are commercial companies, then we would ask you to engage with us in a more formal consulting. The problem with commercial companies asking questions for free is who owns the answer, and if you pay for it, you can own the answer. But of course, if you don't pay for it, then ZP and the world will own the answer. So sometimes it's good to actually just get ZP under a program, so you can actually own the IP. All right, if you've got any questions, don't hesitate to reach out to us. And you can see we put quite a lot of effort into these. All those slides were prepared especially for this talk today. Okay, thanks very much.